So just to give a brief introduction, my name is Brad. I've been working in AI for 5 years now, so not quite a veteran as these people over here, but I've been doing it for a while, and I've also been in software for quite a long time, and especially during my years kind of doing electric brain here, I've worked on a grand variety of projects covering different types of data, image, text, heartbeat data, you know, I like giving these talks. Dragos invites me because just to share a lot of the experience that I'm gaining as I do a lot of these projects. Oh, just one more point. You know, I was super strained to actually fit this into 10 minutes, so I'm not actually going to be able to go over every point I put on the slides. It's like kept doing rehearsals, and it's a lot to fit in. Basically, you know, what I want to talk about today is just, you know, the challenge of measuring accuracy and why people kind of chronically underinvest in, you know, writing the code and to do it properly. And you know, here I highlight a lot of the challenges, or at least the first set of challenges that can come up when you're measuring accuracy. Ultimately, I believe the fundamental problem with measuring accuracy is really that as machine learning is getting better and better and more powerful, the complexity of the behavior that first can happen and that you want to happen is just ever increasing. So some of these problems describe issues that, you know, are very common. You know, you may have different types of failures may be more or less relevant. Your data may not be very good, common in chatbots, or at least in my experience. You know, there may be many different ways of measuring a model that are better or worse. But you know, as machine learning develops and gets more and more sophisticated, you're going to have more of these problems, where you don't even actually have ground truth data, where, you know, a definition of what is a correct result, it's not even clear how to define a correct result. You know, I come back to, you know, how do we measure employees, or how do we measure people and their behaviors? And I think intuitively we all kind of know, you know, I'm not reducible to a number. You know, you can't just, you know, turn me and all of my performance at my job into, you know, one single metric. But that's in effect what we try to do increasingly with machine learning. And you know, as we apply it to more and more areas, it's going to be more and more difficult to come up with even a number that defines accuracy. You know, come up with, you know, how about these models that generate images or music? You know, how do you really define what a good song is? You know, and what a good result is. You know, there's metrics, definitely, like people use entropy commonly with GANs. But I think it just underscores the point that, you know, it's challenging. And so, just breezing through really quickly here, because I only have 10 minutes, what I want to get across is really, you told me only 10 minutes. Okay, geez, no, okay, I can go a little, okay, whatever. Right, good. Yeah, so the thing I really wanted to get across is you can't just, you know, split your data 80-20, compute an F1 score on the testing set and call yourself a day. It's not that simple, and you want to really put thought and effort into the ways that you're measuring and the failure cases and the success cases that your metric actually captures. And so one of the biggest problems, I list a lot of the issues here. Data splits, people commonly do this wrong, where they split their data 80-20 completely randomly when they actually care about generalizing on the time dimension and like doing forward prediction. People often use like metrics that are only at one part of the pipeline rather than the end result. There's a lot of problems that can get in here. So I really want to just convey, like, the most important thing is to think about, like, what are those failure cases and what are those positive cases, and also who's the audience of the metric, actually, just to jump in on the audience piece. You know, if I go to a lot of my clients and I tell them, oh, we did this prediction in terms of classifying your users, and your F1 score is a 0.655. Their eyes are going to glaze over, and they're going to immediately ask, well, what does that mean? Like, what is this F1 score? Is 0.655 good? Is 0.655 bad? I don't know. And suddenly I'm immediately having to put the metric into simpler terms. So I think all data scientists will experience this dichotomy between communicating with their metrics and their measurements of accuracy and the purpose of using a good metric internally. So like if you're communicating a metric to an external stakeholder, the metric needs to be presented and formed from the perspective of a user. So a couple examples of how this can differ. If it's internal R&D, you want to normalize any potential class imbalances that might be present in your data set. Whereas if you're communicating to a user that this is 90% accurate, that 90% measurement needs to be framed from the data distribution that the user is going to experience, which may very well be a highly biased data distribution. And so it's not necessary for you, or in fact it could even make things worse for you to normalize class imbalances when you're trying to communicate to someone who is going to use the model in a class imbalanced way. You go to them and you tell them, it's only 70% accurate, and they experience, in this case the positive, they experience maybe 90 or 95%, they say, oh wow, it's excellent, because they're constantly submitting easy examples to your system. We see this a lot in chatbots where it's like the most common sentences, the 90% are super easy, and then you get this long tail of weird people who just like to hammer out sentences that are like 50 or 100 words long when all they're trying to do is order a pizza. And so, it's easy for me to kind of reflect, you want to reflect the data distribution that your actual users are going to experience. Another thing that comes up here is in internal R&D, you really need your metric to serve as a stable benchmark over time. You need to see, if I do something today and how am I doing next month, I need to know that those numbers are comparable, that I've gone from 85% to 80%. Am I measuring the same thing? So locking in, typically you lock in like a training set or a testing set or both generally. But if you're communicating to an external stakeholder, communicating a metric based on data you locked in 3, 5, or 6 months ago, that's just not meaningful to get. Not only is the number going to be lower because your data set size might be larger, so you're just kind of shooting yourself in the foot in a way, but what the external stakeholder cares about is the production performance and not the not this sort of research metric that serves as a benchmark. So what I think is, we chronically underinvest in designing our metrics. We love to dig into the algorithms and to, either if you're doing deep learning, it's like test different equations and regularization on your network and make it bigger and smaller and wider and whatever. And, the things they do with neural networks nowadays is crazy, actually. But I think we need to put more thought into engineering metrics as well, and to really put effort and to not just split your data 80-20, slap on an F1 score, call it a day. Like it should be something that you design. And so here I discuss many of the ways that you can engineer a metric, evaluate a well-known metric, but only do it on specific subsets of your data. So, for example, imagine you're a self-driving car company. You've got your cars in the field collecting data, but the vast majority of the time that your data is collected on is straight roadways with minimal traffic in sunny conditions, and that could represent 80 or 90% of your data set. Whereas what you care about and what is most important is how well the vehicle performs when it's like turning corners, or when there's heavy traffic, or when there's rain or snow. A common technique is just evaluate your metric on a specific sort of defined subset of your data. Another one, creating a small data set specifically for the purpose of measurement. If you're doing clustering or user profiling, for example, or other types. This also comes up if you have like a long pipeline and you do a lot of post-processing after your machine learning. It may be very valuable for you to actually build up, as tedious and painful as it is, some ground truth data on the final result you expect. So let's imagine you're doing document processing, you pull some data out of a document, but then you run it through some further algorithms that maybe separate it by lines or by rows or columns or whatever. If you only have ground truth data on that middle machine learning algorithm, but not on the final result, you are liable to have a lot of errors in between the machine learning algorithm that you can measure and the final result that you're basically winging it. Applying certain types of augmentation. I know it's of course, a very common technique to apply augmentation when you're training an algorithm, but there may be, in some cases, very worthwhile to actually measure your algorithm on certain types of augmentation as well. Usually not as deeply augmented as you might when you're training an algorithm, but it's something to consider when you're trying to design a metric. Breaking down your metric results by category, this is kind of an obvious one. Making your metric harder and easier. So this comes up for me, again, in document processing a lot, where we have these long documents. They might be very dense with information that we're trying to pull out from the document. And if we have a large training set, it can be very easy to get to a point where almost all of the document is read perfectly. We experienced this when I did receipt processing at Sensible, where you might only have one word mistake on a receipt, if any, at all. So instead of defining accuracy in the document case on a per word basis, because we're already getting like 97 or 98 based on that metric, it might be more fruitful for research to actually make that harder. Instead of saying on a per word basis, we now define the metric as, did the whole document become correctly? Did the whole thing have no mistakes? And so you would expect if you were 98% on a word-by-word basis, you're going to be a lot worse on the whole document basis because it's a harder metric. Same thing with classification problems. We see in image classification, people measure both like top 1 and top 5. So if you start with 1, you may find that your metric is either like close to nothing or very high. You should really consider kind of redefining that metric so that it's better centered, so that it kind of gives you a good signal of whether your model is improving. Modifying your metrics so that certain things considered a failure are counted positively. Again, this comes up in self-driving cars or in chatbots, for example. Another actually interesting example of this is when you have a pipeline of machine learning algorithms. Oftentimes in the middle of the system, certain failures in some middle algorithm can actually be compensated for by a later algorithm. And so you may not actually want to count those as failures at all when you're measuring this system. Some more ways. Changing the way you split your data. Probably one of the most common mistakes that I actually see is people I've said this before, but people basically take their data set, they split the whole thing 80-20, they measure accuracy, and they call it a day. Whereas what they might care about, so this comes up, for example, imagine you're trying to predict whether I'm going to exercise next week. And so you've got a year of data about me, and you're trying to predict, will I exercise next week? If you take your whole data set and split the entire thing randomly 80-20, your algorithm has had data from, say, June or August or September, but is being measured on March, April, May. So this is not the operating environment that your real algorithm is going to be in. Your algorithm never has data from the future to learn on to predict items from the past. What you should have done, in my opinion at least, is you should have split on the time dimension, because you should have split, say, I'm going to predict March and April based on all of the data that I had previously. Another place where the splitting of data comes up is when you're joining different database tables. So sometimes people make the mistake where I'm going to join these 3 database tables and then I'm going to do an 80-20 split on your data. And this kind of ignores the problem that your model could be overfitting to any one of the samples in these tables. Because if you split only kind of joined result, 80-20, the data from any one of those tables may be in multiple entries. And so if you do the split on just the joined results, your model could still be memorizing the data from any one of these tables. Instead what you want to do is probably split the original data in the original database 80-20 on each of these 3 different tables, then join and construct your testing and training data sets. Normalizing your metric, this comes up in all sorts of kind of more novel cases, if you've got a minimum or a maximum size, if you're trying to predict, say, real estate prices, just computing like a mean squared error is just not that useful. You might be better off to do mean percentage squared error, which would, in this case, normalize. So, you're considering houses that have a low value, let's say $100,000, and houses that have a high value at $1 million. You don't want to weight your metric more towards the $1 million house and your measurement of accuracy more towards the $1 million house just because it's $1 million. So normalizing the metric to be like, what is my error as a percentage of the house price can help you there. Modeling your model's performance relative to a benchmark. Let's say you have a model that you already know performs really well. This came up for me when people are trying to shrink models onto the cell phone. So you might start with a model on your laptop, and it's a really big network and really computationally expensive, but you got it working. Like, you got great results. You validated the accuracy. One of the options that you have is like when you're trying to shrink that onto the smartphone. Yeah, you can measure on your original training set, but you could also measure against your laptop model. And what this allows you to do is actually use all of your unlabeled data as a benchmark. So say you have only a limited amount of labeled data that you're training your desktop algorithm on, you can then run that algorithm on the unlabeled data, and then you have a much larger set against which you can measure the smartphone that kind of shrunk, the results of the shrunk model. Creating a hand-coded validation routine. Coming back to receipts, we had a simple way of measuring accuracy that didn't need any ground truth, which was to make sure the numbers we extracted all added up to the total that we extracted. And if that was ever wrong, there's actually cases where that was wrong. Apple and Walmart are have weird receipts sometimes, but for the most part, the numbers on receipts should always add up to the total. And so like we can apply this validation routine. It's not perfect as a metric goes. It can make all sorts of other mistakes and not be labeled wrong, but its advantage is that we can apply it without ground truth data. And of course, creating your own statistical equations. Sometimes you're just in a really weird situation, and you particularly with GANs, if you're trying to apply a GAN into a new area, you don't have like an inception score if you're trying to develop something like generating blueprints of buildings. So you may have to kind of come up with your own system, and it should be within your toolkit, your arsenal of options to create your own equation, to really go outside the boundary instead of just using a scikit-learn function that you can read the documentation for online. In conclusion, better measurement means better models. When you make mistakes on measurement, you inevitably will end up putting a model into production that you later have to revoke, or you later have to explain to some stakeholder as to why it's performing significantly worse than expected. And you can also get really confused. Like, you can confuse yourself by doing poor measurements and doing things really quickly. But usually, very rarely does a poor quality measurement mean that your model actually is really good when you thought it was shit. I wish that happened, but the reality is a bad measurement almost always tells you your model is amazing when in reality it's shit. And so having a better measurement allows you to avoid that situation, you know. Don't overwhelm yourself with a lot of metrics. I have blog articles on the topic of measuring accuracy where I go into this one a little bit more. But you know, if you have a big complex machine, it's easy to go in the opposite direction and just turn yourself into metric salad, having precision and recall and accuracy and F1 score and this and that, and doing it by each of the classes, and then doing it all of that at each stage of the pipeline, and doing that on training, testing, and validation, and out of sample. And pretty soon you've got hundreds of metrics, and it's impossible for anyone to know what the heck is going on. So rather than doing that, which is easy to do when you're writing code, but is not very, very useful, spend the time to actually think about your metrics. Spend the time to think about the failure cases that your metric considers, the failure cases that it might ignore, the weighting that it's applying to different failure cases. And another thing that I forgot to mention is that you should consider at least having 2 metrics in all projects. One metric for your research purpose, and a completely different metric which serves your communication purpose. They're measuring the same thing, but the communication metric, it really needs to tell a story. Like, if I'm talking to a client, they're a business person, and I tell them it's 90% accurate, I want them to be able to put themselves in the shoes of someone interacting with this model and seeing it fuck up and seeing it succeed. You know, if I go to a client and I tell them, you know, our entropy measure is 0.67 and our F1 score is 0.85, there's no hell in a way that they're going to imagine themselves using that model and interacting with it. So spend the time to design a small number but of thoughtful metrics, and at the very least, you know, differentiate between the metrics for the research purpose and the ones for that kind of stakeholder communication purpose. And that's it. That's all I have to say.